Once again, welcome everyone. My name is Arya Hakimian. I'm an application scientist here at C-Therm Technologies. Today's webinar, we will be focused on the thermal effusivity determination of wet textiles. This will be some work presented by some guest speakers we have online today. Both from the University of Alberta, Patricia Dolez and Rashedul Islam. So we'll be going over some of the research work and developments that have been done within the effusivity of these wet or saturated textiles. So before we jump into that, I'll just aim to do a little bit of a background introduction to C-Therm for those of you who may be new. Want to give you a little flavor for some of the other aspects of what we do here, and then of course go into some additional details on thermal effusivity as it relates to fabrics and textiles. So C-Therm Technologies, we're a Canadian-based company with specialty in the range of transient methods for thermal analysis. So thermal conductivity, thermal diffusivity, as well as thermal effusivity. This is really what we focus on here. Our flagship product is called Trident. So you can see a picture of that here. So Trident was developed as a modular system. It is one instrument platform that brings together multiple methods for thermal characterization. Really depending on the type of sample you're working with, maybe the testing conditions you're looking to replicate, really gives you some options there to pick the best tool for the task at hand. And this quote here really embodies the idea behind Trident. This is a famous quote from Abraham Maslow: "When all you have is a hammer, everything looks like a nail." And this really speaks to some of what we've seen in industry. The probably biggest source of poor data is when you take a really good method, but try to apply it in a scenario that it just wasn't designed for. So again, really being able to pick and choose the best tool for the task at hand really gets you to your best possible outcomes with respect to the data. Now, of course, here today, we're looking at a very specific topic, textiles, thermal effusivity in particular. And this is all going to be done under the focus of the MTPS, or Modified Transient Plane Source. So you can see a picture of the sensor here. Big high-level takeaway here is that the MTPS provides both thermal conductivity and effusivity data as your output. And when we're talking about textiles, fabrics in particular, really the use of the ASTM D7984 is something that is very broadly adopted for the performance characterization of those materials through the effusivity measurement. Now, ASTM D7984, you can see here, this was established, again, standard test method for the measurement of thermal effusivity of fabrics using the MTPS. This standard is, again, very great for broad characterization of these types of materials. However, one thing just to mention, these are all under the dry state. So there's certain requirements. There's a lot of information in the standard that you can get to give more details on the standard operation and things of that sort. But where we're going to get a little more novel here today is, again, where we take the aspect of wetting, and again, specifically some of the work that the University of Alberta is going to present on today. So really, ASTM D7984, a great basis for kind of the standard characterization, but we'll see some very more novel testing options using the MTPS and effusivity, but under a different state here in the presentation that will follow. So what is thermal effusivity? For those of you, again, maybe some background, or maybe this will be review for those of you who know, thermal effusivity, sometimes referred to as thermal inertia in literature, but essentially it describes a material's ability to exchange heat, thermal energy, with another body that it's in contact with. Knowing different aspects of properties of, or different material effusivities and the temperatures, you can do things like calculate surface temperature upon contact. But this fundamental idea comes into why we're using effusivity as a performance metric for this class of materials. What it really helps us do and understand is that touch perception of the different materials in play, whether they are more warmer feeling or cooler touch. So this is a general call it performance index. You can see, on the low end, Lower effusivity values will correlate to a more warmer feeling or cozier sensation. And as you increase in effusivity, you get into more of that cooling sensation. So this is a really great way of baselining performance for different materials. A lot of groups in the sports and apparel industry, looking to bring different materials into various product lines. Of course, if you're in the summer when things are really warm, you want to have materials that are going to be on that cooler side for the comfort aspect. But, if you're developing something for a winter wear, jackets, something, fall clothing, you're going to be probably looking at some of those warmer feeling fabrics. And you can see some general examples here. But as we can see, as you go up on the very far end, we have water. So anytime there is a saturation aspect in the material, this will impact the effective thermal conductivity, thermal effusivity of that material, and again, drive that perception in different ways. So again, looking at just the general material performance through effusivity in the dry state is a great kind of baseline. But when you start to add different moisture, different saturation levels, this is where we can see some interesting behaviors in the material. And again, really what's going to be focused on in the latter part of today's session. Another thing that you could maybe make use of effusivity for is in claims validation. So maybe you're not necessarily, in the R&D side, developing different materials for these different product lines. Later on downstream, to be able to make certain claims, you'll see things like cool to the touch, helps keep you cool, etc. Some of these can be backed up through the measurement of effusivity and using that to help, whether it's with the hang down tags you see in real retail stores or what have you. So these are just a few kind of areas where the effusivity can come into play. So before I kind of close out this kind of brief introduction, I will just flag, so at C-Therm, of course, the thermal properties of the material, what we focus on with Trident. We are also partnered with Rigaku and Metrobib to offer a variety of other thermal and mechanical property testing capabilities. If you have any additional needs, maybe you want to explore a few different areas in your research, certainly happy to support you in those endeavors. And we also have a full service contract testing lab, thermal analysis labs. If you're looking to have some samples sent out on a contract basis, we can certainly help support those discussions. So if you'd like to learn more about any of that, please feel free to reach out. We can schedule a call, get us set up with kind of understanding your application needs, provide any budgetary information, and of course, go from there. Last thing I'll end is with a client testimonial. We always like to really talk about what our clients are saying. This one here I just picked is from Fang Wang, who is a lead material scientist at Kimberly-Clark, noting that the MTPS sensor is a fast and accurate instrument, which has been invaluable in their lab. The MTPS allows them to quickly understand the thermal properties of their non-woven textile materials, diapers, and wipes, just as an example. So we do have a full client testimonials list on our website if you'd like to check that out and kind of see where different researchers in different industries are using the equipment and what they have to say about it. All that being said, I am going to cut my section here because, of course, the star of the show will be Rashedul Islam. He will be coming on to present some of the work here in the wetted textile characterization space. Myself, Rashedul, as well as Patricia will be available at the end for the Q&A. So again, if you do have any questions as the presentation goes on, please feel free to make use of that chat box feature. All right, so with that being said, I'll stop sharing here. Rashedul, please feel free to take over.
Thank you, Arya, for introducing me. So I'll just share my screen right now. Okay, so can you see my screen?
Perfect.
Okay. So, yeah. Hello, everyone. Good morning, good afternoon, and good evening from where you are. My name is Rashedul Islam, and I'm a PhD student in textile science at the University of Alberta. Today, I'm going to talk about thermal effusivity test method development for sportswear fabrics. And this study was supervised by Dr. Patricia Dolez, who is an associate professor at the University of Alberta, who is here today, and also by Dr. Kevin Glovin, who is an assistant professor at the University of Toronto. And in this project, we collaborated with C-Therm. So without further ado, let's get started. So Arya already have give some definition and brief introduction on thermal effusivity. I'll also go over it briefly, and then I'll start talking about my results. So first, what is thermal effusivity? The term thermal effusivity can be defined as the warm or cool touch sensation or thermal touch perception due to the heat exchange between two surfaces. For instance, if we have a wooden ball and a metal ball at the same temperature, for instance, 20 degrees Celsius temperature, and if we touch them, then the metal ball would give us more cool touch perception than the wooden ball. This is because there is a greater amount of heat exchange between the metal ball and the human skin. And then the thermal effusivity value of metal ball would be higher than the wooden ball because of this higher amount of heat exchange. Why thermal effusivity of fabric is important? Thermal effusivity of fabrics is important because it affects homeostasis of a human body. For instance, thermoregulation like vasodilation, vasoconstriction. It also helps in protection from environmental extremes such as heat and cold stress. It also helps in sensory feedback such as injury prevention, like when we're touching a heated surface. And then also it affects comfort and quality of life. For instance, if we're sleeping and we're feeling colder, it's going to hamper our sleep. And also thermal effusivity is going to affect our work performance. Now, how is the thermal touch perception of fabrics assessed? So previously, thermal touch perception of fabrics was assessed by subjective evaluation. So in this case, the fabric patches were attached to the human body, and then the human participants were asked about the touch perception of the fabric, which is labor-intensive, time-consuming, and also very expensive process. And that's why scientists came up with objective measurement by instrument, like the objective measurement technique for the thermal touch perception. So in this case, we can use thermal effusivity tester. So on the right side, we have the instrumental setup for the thermal effusivity tester. So this is C-Therm thermal effusivity tester. And we can use this thermal effusivity tester to measure the thermal effusivity of fabrics based on the ASTM D7984 standard test method. And according to the test method, the pressure range for conducting the thermal effusivity measurement is 10 to 50 kilopascal. So this pressure is applied by the pressure foot here. And also we see here, we have a fabric stack. So according to the standard, the stack height of fabric should be at least 1 millimeter because the MTPS sensor, it releases a pulse for the thermal effusivity measurement, and that pulse has a height of 1 millimeter. So here we see the fabric stack, and it has at least 1 millimeter height because due to the standard suggestion. So now I'm going to talk about the objectives of this research study. The first objective was to develop a method that closely resembles the actual wiring conditions. For instance, if we look at this stack method, it doesn't resemble the actual wiring condition because if we think of single layer sportswear fabric, in this case, one side of the fabric touches the human skin and other side is exposed to air. And in the stack method, this is not happening. So that's why we wanted to develop a method that closely resembles the actual wiring condition. And the second objective was to develop a test method to determine the thermal effusivity of fabrics in the wet state, because currently there is no existing test method for the thermal effusivity of fabrics in the wet state. In terms of material, we have worked with 27 sportswear fabrics, and these 27 sportswear fabrics includes woven fabric like plain weave, knit fabrics such as single jersey, interlock, jacquarded, tricot, work knit, and fabric contents included cotton, nylon, polyester, lyocell, exstatic, coolmax, elasto, multiester, polyester fibers. So these fibers are mainly used in sportswear fabrics, and also thickness varied between 0.0 0.083 to 2.19 millimeter. So depending on the objectives, today's presentation is divided into two topics. The first topic I'm going to present is titled Thermal Effusivity Measurement of Sportswear Fabrics in the Dry State, Stacked and Air Hoop Method. So on the left side here, we have the stacked method arrangement. So this is the standard method arrangement. And on the right side, we have the air hoop method arrangement. So this is the new method we worked with. So in this case, instead of the pressure foot, we have used air hoop frame. So this is consisted of inner ring and outer ring. And in this case, we worked with single layer of fabric. So the single layer of fabric specimen was attached to the air hoop frame. And then one side of the specimen was touching the sensor, like the one side of the fabric touching the human skin and other side is exposed to air. So this air hoop method, it closely resembles the real wearing scenario of single layer sportswear fabrics. So now I'll dive into the results. The first, we investigated the effect of applied pressure on the thermal effusivity measurement. So along y-axis, we have the thermal effusivity measured using the stack method. Along x-axis, we have the applied pressure. And in this graph, we have the results of first 4 fabric among the 27 fabric F1, F2, F3, and F4. And we also conducted the measurement outside of the standard range of pressure. Previously, I mentioned that the standard pressure range is 10 to 50 kilopascal. But we also conducted experiment at 0.5 kilopascal, 1 kilopascal, and 2 kilopascal. So from this graph, we had some findings. The first finding was that, so when we increase the pressure, thermal effusivity value of fabrics increases. And also at 50 kilopascal pressure, because it was compressing the fabric, we actually obtained the material-based thermal effusivity rather than the fabric thermal effusivity. And also we worked with the air hoop method with the 4 fabric. In this case, the applied pressure range was 0.5 to 2 kilopascal. We didn't go over the 2 kilopascal pressure because at 2 kilopascal pressure, it was already stretching the fabric from the normal condition, which was changing the fabric porosity. So also from this graph, we found that there is an effect of pressure on the thermal effusivity results. And the main finding of these two graphs was that 1 kilopascal pressure was the optimal applied pressure for both methods, as it allows performing the measurement while preserving the fabric's 3D structure. And then after measuring the thermal effusivity of fabrics at 1 kilopascal applied pressure both for the stacked and air hoop method using 27 fabrics, we investigated the correlation between them. So in our correlation and analysis, we found that they have a strong correlation for fabric thicknesses close to or greater than 0.4 millimeter. So in this case, only fabric F16 became an outlier. This is because the fabric F16 had very extremely low thickness, which is 0.083 millimeter. This is very low compared to the pulse height of the MTPS sensor. And also another finding was that air hoop method better simulates the situation when the fabric is worn as part of a single layer garment. And then we investigated the relationship between the fabric's thermal effusivity measured using the air hoop method at 1 kilopascal applied pressure with the thermal resistance of 27 fabric measured using the sweating garnet hot plate with perpendicular airflow on the fabric surface. And in this case, we see that the reciprocal square of the thermal effusivity of 27 fabric has a linear relationship with the dry thermal resistance of fabric. This is because both the dry thermal effusivity and dry thermal resistance, they depend on the thermal conductivity of the fabrics. So that was a brief presentation on the first topic of my results. And the second topic I'm going to present is titled Thermal Effusivity Measurement of Sportswear Fabrics in the Wet State. So now I'll just give some brief introductory information about the wet thermal effusivity. So first thing is that wet fabric causes an increase in heat loss from the human body, which creates a cool touch perception. It can be pleasant for some situation, but may lead to discomfort in other situation. And also a limited number of studies investigated the thermal touch perception of fabrics when they are wet. most of these studies explored this phenomenon in terms of wetness perception through wire trials. So the objective of this second study was to develop a systematic approach to quantify the thermal dust perception of fabrics in terms of thermal effusivity at various water saturation level, and then also to explore the relationship between the thermal effusivity of wet fabrics and the amount of water absorbed and the saturation level and other fabric properties. So the study was conducted in 3 steps. First, we developed the weighting protocol for conducting the measurements. So then we conducted the thermal effusivity measurement. And finally, we did the correlational analysis. So now I'm going to talk about the weighting protocol for the 25%, 50%, and 75% saturated specimen. So among 27 fabrics, some fabrics had good moisture wicking ability. For those fabric, first I sprayed water on both sides to reach the desired saturation level. If the amount of water is more on the fabric, then we let the fabric specimen dry on a flat screen. And after that, the fabric specimen was kept inside the airtight plastic bag for moisture equilibration, so that there is proper swelling of fiber yarn within the fabric structure. And this was done for like 12 to 24 hours. And for those fabric, those had like poor moisture wicking ability, those kind of fabric was dipped in water for 2 minutes. And then we let them dry on a flat screen. And after that, the fabric specimen were kept inside the airtight plastic bag for the moisture equilibration. And after that, the next day we conducted the thermal effusivity measurement on the saturated specimen. So now in this slide, I'm going to talk about the weighting protocol for the 100% saturated specimen. So this protocol is different than the previous one. And there are 7 steps for the weighting protocol at 100% saturation level. And it is important, it is very crucial to maintain all those steps to obtain consistent results at 100% saturation level. So first, we dip the fabric specimen in water for 2 minutes. And then we took out the fabric specimen from water by using a tweezer, and then we did water dripping for 1 minute to remove excess water from the fabric specimen. And then we kept the fabric specimen inside the airtight plastic bag for moisture equilibration and proper swelling of fiber and yarn within the fabric structure. So this was done between like 12 to 24 hours. And then the next day, the fabric specimen was collected and it was attached to the air hoop frame. And again, the fabric specimen is dipped in water with the air hoop frame for 2 minutes. And after that, the air hoop frame was taken out from water, and then we did sidewise stripping to remove excess water. So we made sure that nothing touches middle area of the fabric surface, because if there is any transfer of water between the middle area of fabric surface to any external object, it's going to harm the reproducibility of the results. And after that, we kept the air frame upside down on a hollow cylindrical platform for moisture equilibration just for 1 minute. And after that, we conducted the thermal effusivity measurement for the 100% saturated specimen. So now I'm going to dive into the results again. So first, we investigated the thermal effusivity results of the first 4 fabric at various saturation level using the air hoop method. So we see that with increasing the saturation percentage, thermal effusivity of fabrics increased. And we also see that above the 75% saturation level, so there is a sharp increase in thermal effusivity. So this is possibly because of the formation of thin layer of water on the fabric surface between the 75 and 100% saturation level. So here I am going to explain the possible mechanism. So below the 75% saturation level, fabric specimen might have enough space within its structure to retain water molecules, so the water molecule are getting inside. But between the 75 and 100% saturation level, there are some spaces for water molecule to get inside the fabric, but in other cases, water molecule are staying on the surface of the fabric, so they don't have a space to get in. And at 100% saturation, fabric specimen is completely saturated, so there is no space inside the fabric structure, and the thin layer of water is started forming on the surface of the fabric. And then we investigated the thermal relationship between thermal effusivity at 75% saturation and below with the fabric dry thermal resistance. So here we see along y-axis we have the wet thermal effusivity at 25% saturation level. 50% saturation level and 75% saturation level. And along x-axis, we have the thermal effusivity of fabrics at 0% saturation. That means the dry specimen. So dry thermal effusivity along x-axis. So in this relationship analysis, we found that the wet thermal effusivity of fabric at 75% saturation and below have a positive linear relationship with the thermal effusivity of fabric of those fabric in dry state. And there can be two possible reasons for that. The first possible reason is that water is homogeneously distributed across the fabric volume at 75% saturation and below. And also the second possible reason is that water affects the fabric characteristics that control thermal effusivity in a similar way for all fabrics. And the final conclusion was that this relationship allows us estimating the wet thermal effusivity at 75% saturation and below from the dry thermal effusivity value of those fabrics. And then we investigated the relationship of thermal effusivity at 100% saturation with the amount of water that is present in the fabric at 100% saturation level. So along y-axis, we have the 100% saturation thermal effusivity. Along x-axis, we have the water content in the fabric at 100% saturation. So we see that they have a nonlinear positive relationship. And this relationship is like this trend is similar to the trend that has been reported by Recuglia in 2017. So where they studied the relationship between the wetness perception of fabrics and the mass of water that is present in the fabric at 100% saturation level. So that was a brief presentation on this second topic of my today's presentation. So now I'm going to talk about the overall conclusion of my presentation. The first conclusion is that the applied pressure range indicated in the ASTM standard compresses the fabric and it leads to the material-based thermal effusivity measurement. And also here we propose the 1 kilopascal applied pressure because it allows the preserving fabric 3D structure. The results with the air hoop method were validated by the wire trials study of the wetness perception of fabrics from the literature. And we also showed that the air hoop method can be used to better simulate the fabric's thermal touch when worn as part of a single layer garment. The third conclusion was that the thermal effusivity of fabrics at up to 75% saturation can be estimated from the dry thermal effusivity value. And the last conclusion is that the thermal effusivity of fabrics at 100% saturation can be predicted from the amount of water that is present in the fabric at 100% saturation level. So with this, I want to end my today's presentation. Thank you so much for listening to my presentation. And I would like to acknowledge Dr. Jane Batchelor and Protective Clothing and Equipment Research Facility at the University of Alberta for training me with different equipment and also for giving me access to the lab. And also MyTax, Lululemon, INSERC, and CFI for financially supporting my PhD project. Thank you.
All righty. Thank you very much, Rashedul. Appreciate that. Okay, folks, so just wrapping things up here, just a quick little outro before we go into the Q&A session. We'll go through this pretty quickly here. So, these types of webinars, again, we put these on quite regularly. Similarly, a lot of the resource materials that are part of these sessions, they're all available on our website at www.ctherm.com. Definitely feel free to check those out if you'd like to see maybe some similar work that's been done in the past or in other areas of application as well. If you want to keep up to date with us for, upcoming webinars, blog posts, other content pieces, LinkedIn is certainly going to be the best place to do that. That's where we post all of our newest, latest and greatest on there. So if you're not already giving us a follow, please feel free to do so. I will just flag for the upcoming webinars. Going to be none more in the textile space, but again, some related different areas of application coming up. We have quite a few over the next month. So first one there on September 5th, we'll be taking a look at the thermal performance of a variety of polymer-based materials. These are filled. It's part of our conductive filler series using transient techniques. A little bit later in the month, September 19th, we'll have another guest speaker. It's from MG Chemicals coming in to talk about some efforts that are being done on reworkable thermal interface materials. And then we also have more of a fundamentals series in the works as well. So September 17th, my colleague Genesis will be taking us through some dynamic scan and calorimetry DSE theories and applications. And then at the beginning of October, I'll be doing another fundamentals series, really looking at some of the more basis ideas behind transient thermal conductivity and some related applications. We'll also be at some upcoming events. If you're in the area and, of course, you're able to stop by, we'd love to have a chat. Got a few there listed. So September 9th to 12th, we'll be at IEC. That's going to be in Pittsburgh, Pennsylvania. We do have a booth there, so please feel free to stop by if you're going to be around. September 16th to 19th, we'll be at NATIS. That's going to be held in Knoxville, Tennessee. And then at the end of the month, September 25th to 27th, we'll be at the K Battery Show in Korea. And again, similarly, we have a booth there as well. So that brings us to the end of today's session. I would just like to thank everyone in attendance for joining here today, as well as to our guest speaker from the University of Alberta. Very appreciative of coming on and talking about some of the work that's been done there. So for the folks that are still on the line, we will now go into a Q&A session. So if you are interested, please feel free to stick around and definitely go ahead and post any questions that you may have. All right. So let's see here. Questions. Yeah, Rashedul and Patricia, I invite you to join me on screen here. I'll kind of go through. I'll kind of direct these questions. So one comment here. So someone has their hand raised. So we're not able to do. If you have a question, please type it into the Q&A, the question feature there, and we'll answer that. I just noticed someone had their hand up. All right. So first one, excellent presentation and work. Can we know the thermal perception value from thermal conductivity according to thermal effusivity's expression of conductivity? So I guess it's related to, asking about using thermal conductivity or effusivity for the characterization of these materials. I'll just say from my side, generally speaking, when we're referring to thermal with the touch perception, we typically relate it to the effusivity. If you're looking at materials across a broad range of different applications, generally speaking, if you notice an increase in one, they generally correlate together. But yeah, for fabrics, especially according to these standards and the basis, it's generally related to the effusivity there. Rashedul, I believe most of the work that was done on yours, it was all under the basis of effusivity, correct?
Yeah, thank you so much for your question, Shakil. And yes, Arya, so you are right. So I can add here one thing is that, so when we can calculate the thermal conductivity from the thermal effusivity, they are correlated through equation, but there is one thing, thermal touch precision is only giving close to the surface feeling. But when you are thinking of thermal conductivity, it's if we have more thickness of the fabric, thermal conductivity would be the same. If we have the thermal conductivity never change. If we have the multiple stack, but thermal effusivity is going to be changed. It's just only the feeling of the surface. And whereas thermal conductivity is the whole thing of the
Exactly. Perfect. So a question. Oh, sorry, Patricia.
Maybe, and if I can add something. When you're looking at thermal effusivity, it's not just thermal conductivity. So in fact, there's other parameters, the densities, the heat capacity that are sort of taken into account, and this may differ. I mean, I would say that in terms of textiles, density may be similar, but still there's maybe some differences. The type of textiles, if you're adding, I don't know, metal fibers, or you may have some differences. So I think that's why, in a sense, thermal effusivity gives a sort of a closer perception to what the human skin will get.
Thank you. Next question here. So, what was the size of the test sample and how much water was used across the saturation levels? I'll throw that one to you guys.
So I can go ahead and answer that question. So in terms of sample size, we have used 10 centimeter by 10 centimeter. And then how much water? So like first we determine what is the amount of water for 100% saturation level. So for that, we dip the fabric specimen in water for 2 minutes. And most of my fabric, like among 27, like 26 fabrics, they reached their like the 100% saturation within then 2 minutes. And then we took out the fabric specimen from water. We did 1 minute hanging to remove the excess water. And then we measured the weight of the saturated specimen. So we have the dry weight and the saturated weight, and then we subtracted them, and then we found the amount of water for 100% saturation. And then we divided with like the 4 to get 25% saturation, and the amount of water for 25% saturation, 50% saturation. That's the way we did it. And for the method we followed, so there is a ISO method for the water absorbency measurements. We actually followed that method for the saturation level. Yeah.
Thank you. So another question I think maybe somewhat related. So the level of saturation of the fabric is measured on the basis of water absorbed, or was there another method? I think you somewhat answered that, but.
Yes, so there was like the ISO method. I will just look at it, and I don't remember the exact number. I can share the number, like, yeah, just like after a few minutes. Yeah.
Question here, what is the sensitivity range of thermal effusivity as it correlated to consumer response? So I think that was a little outside of what you were looking at as far as like that side of things. I will mention that's somewhat akin to some work that we had actually done with a different research group on a different project. The University of Oregon. We actually did a study the other, few years back now, I guess. Time flies. But there is some information gathered there about when a material becomes more enters into that warmer feeling state versus the cooler, cool touch perception. Michelle, yes. Someone from the team will be able to follow up. We might actually can send you like a link to where that publication is at, so you can take a look at that in further detail. I guess just as a note for anyone that's answered a question or asked a question, we have a note of anyone here that did have an inquiry. So any additional follow-up, someone from our team will be able to direct that if you need some more information. Okay, another question here. Thank you for the presentation. Can you name a ASTM standard for the air hoop method of measuring thermal? Is the working principle of MTPS and air hoop method the same? So I'll say, so the ASTM D7984 standard as written, and again, as Rashedul presented on that first piece, it is with that stacked that minimum thickness with the pressure foot in contact there. The air hoop is a really nice accessory that can be used, and again, provide some more representative testing in certain applications, looking at that, having air as the backing, how that impacts. And again, really what was used for the wetted work. It wouldn't be, I'd say, part of that ASTM standard as written, though.
So can I add something?
Sure.
Here? So yeah, like we also try to follow the stack method for the wet thermal effusivity measurement, whether it works or not. So in our experiment, we found that it doesn't we had very hard time to obtain consistent results with the stack method, because when there is like multiple layers of fabrics and then there is like water between the layer of fabric, and it's hard to control the amount of water between the layers of fabrics. And we were not actually able to obtain the consistent results with the stack method. So that's why like we came up with this like realistic, like more realistic, like the single layer method.
Okay, another question here. So hi, we have this person has a Trident with MTPS. I've tried to measure the thermal conductivity, so looking at conductivity of coated and uncoated fabric, semiconductor-based fabrics. I'm getting results 0.5 to 0.7 watts per meter Kelvin. I have searched for papers regarding the range of fabrics I could be able to get the research paper in this range. So could you help me getting it and for the silver fabrics also? If I'm reading that correct, I will say, so if you're testing something that's got more of a conductive or, higher conductivity, higher effusivity basis to the material, having that, I'd say relatively higher result somewhat would make sense. The big thing, I guess, in any fabric, of course, is the overall construction. One of the things that I've seen in testing a variety of textile materials is you could have a cotton sample, you could have 10 of them, but if there's differences in the construction, some of the yarn sizes used, that can impact the overall results that are obtained. Nanthini, I'm sorry if I'm pronouncing that incorrectly. Someone from the team, I think could definitely help by following up with you on more of a one-on-one basis so we could kind of get some more information on the research that you're doing. But we'd certainly be happy to be a resource to you in the future. Thank you for the wonderful presentation. I have a question related to the wet thermal effusivity. For the 100% saturation level using air hoop, how would you control the excess amount of liquid attached to the hoop and also confirming it's not affecting your saturation level? So Rashedul, I think you spoke about that in the kind of the steps involved with the side or the side dripping, but any additional comments maybe to that question?
Yes, thank you so much. So actually, for these consistent results, like we did multiple trials for 100% saturation level. So initially what we tried, we created the 100% saturated specimen with water, and then we kept inside the plastic bag for conditioning. And then the for moisture equilibration, and then next day we attached it to airframe. So when we took out the fabric specimen from this the airtight plastic bag, so there was some transfer of water between that plastic bag and the fabric specimen. And then we came up with other ideas. What if we just saturate the fabric specimen and don't condition do the moisture equilibration, just attach it to airframe. So we also did that, but then we had some problem the proper swelling. We didn't get the proper swelling because it was limited on for limited time. So then finally we combined both methods. So now I'm going to just an explanation on the final method. So in the final method, we create this saturated fabric specimen and we did moisture equilibration for proper swelling. And the steps involved after the proper swelling, though in those steps, we made sure that nothing touches the surface of the fabric where we want to do the test, in the middle area of the airframe. So that part of the fabric we never touched. And then we try to maintain this whole protocol. We first need to dip in water for 2 minutes, and then we did sidewise water dripping to remove excess water. So that 1 minute was enough for remove the excess water. And then we kept the airframe upside down on a hollow cylindrical platform. So when we did it the upside down, so because of the gravitational force, when initially we did the sidewise dropping, and after that we did the upside down. So there was the even distribution of water throughout the surface. And we always maintain that nothing touches the middle area of the fabric for the test. So that's how we were able to obtain consistent results.
Thank you. A few more questions here. Excellent talk, Rashedul. I agree. The instrument and method are for through plane. Is that right? In reality, would there also be in plane spreading? So I'll say from the MTPS, yes, you are correct. The MTPS, and based on some of the guard ring principles, the actual design of the sensor is providing that through plane measurement. There's a directionality to the measurement itself. The effect of the in-plane heat spreading, it is something that come into play, of course, in anisotropic material characterization. I think from our side, what we've seen is, of course, trying to use the method as a baseline to at least generally understand that material performance. There's potentially, of course, a variety of directional properties in a material and can vary from material to material as well. But yeah, this is all under the focus of through plane measurements. Rashedul, I'm not sure, like maybe in some other side of things or some other studies, is that something that you've ever taken a look at, or mostly just with the through plane characterization?
Mostly I did like through plane characterization.
How the effusivity varies if the fabric is having more open regions like pores seen in sport tees compared to a solid fabric. So I'd say generally speaking, the evaluated volume of any technique has an impact, right? So if you have something that's quite like solid in construction versus something that's more open pore, open fabric. Similar idea under compression. If you have something that's very loosely compressed, of course, there's going to be more space versus if you compress it down, you're really pushing that material in direct contact, right? So that can impact the thermal properties of the material. Generally, the more air that's going to be present in any evaluated volume will have a net decreasing effect compared to something that is less or more compacted in nature. And any maybe additional comments from your side, Rashedul, or?
No, I think I'm good. Yeah.
Yeah, maybe I can add that one thing that Rashedul showed is when we're looking at the wet thermal effusivity, it was correlated to the amount of water that is contained into the fabric. And the amount of water that is contained into the fabric will then be correlated with the fabric density or the type of yarns or things like this.
Gotcha. All right, one final question here. So lots of good questions from the audience. Thank you everyone for those. At what test temperature was the testing done? And what is the temperature dependence of effusivity on the effusivity measurement? Maybe if you wanted to speak to that first point there where you did the testing.
Oh, yeah. So I did the test at like 20 degrees Celsius temperature for the C-Therm sensor. Also, like the ambient temperature was like 20 degrees Celsius. But so because like in the standard they mentioned as like similar temperature is like 21 plus minus 2. But I think in future, like I'm not sure like who is going to work on that, but like we are going to work with high temperature, like 35 degrees Celsius close to skin temperature.
Yeah, perfect. Yeah, I know there has been most of the work I'll say that I've done with textile characterization has been generally around that. I do know some groups have explored the lower and upper temperature range, and the impact that would have on the overall performance would be dependent on the materials involved, of course. Some materials, as you increase in temperature, they're, for conductivity, for example, you'll see an increase. Others will have a decrease as a function of temperature. But yeah, so most of the work here is done around that 21, but definitely a good idea for some additional work there. Okay, so that brings us to the end there. Thank you everyone for the questions. Thank you Rashedul and Patricia once again for not only presenting, but going through those questions with us here today. Really appreciate that. I guess at this point, we can go ahead and close out this session for here today. Once again, thank you everyone for